reduction set or the class material direction thickness inequalities proof, but after that I didn't read that algorithm.
Oh, we need one scribe. Anyone? Oh, okay. Thanks. Yes. All right. So let's start. So last week we were talking about we see for the first time the connection between eigenvalue and expander. So basically, a graph is we see it from Cheeger inequality. It basically says that the graph is an expander, or it has high conductance, if and only if the second eigenvalue of the normalized Laplacian is bigger than 0. Yeah. Right. So that this is like the relationship, the precise relationship between them, and from here, we also see that, okay, just from the proof of Cheeger inequality, we see how to get actually a cut. Because it says that if a second eigenvalue is small, then there must exist a sparse cut. And we show that how to find such a cut, actually, such a cut S that have conductance at most this. Or approximately that, approximately this. Like, in class, we show how to get something like this thing, this bound. So this is a good approximation if phi is not too small. Otherwise, it's not too good. So today we're gonna continue a bit more on this spectral view, like perspective from eigenvalue, and first thing, I will talk about like how to compare graph based on Laplacian. And the next thing is about saying that although this message of saying that the graph have high conductance if and only if second eigenvalue is high, this is a bit rough. There is some special property of expander when the expander, like when the graph have high eigenvalue, there's some special property that it satisfies when this graph have high eigenvalue, but it doesn't really satisfy when the graph have high conductance. So it's like there is some like details when they are different. Okay. So first thing first, I would like to tell you about this. Like I would like to compare the graph between compare the graph H and G with respect to spectral sense. So we said that H is less than G if X times, like if for every vector X Laplacian of H times X is less than X times Laplacian of G times X. Okay, so that is just like a way to compare graph. Okay, so note that just to connect it to like some linear algebra background, this thing is true if and only if LG this thing is always at least 0, which means that this thing is positive semi-definite. Yeah. And we also like when people also write it like this, just to say that LH is less than L of G when LG minus LH is positive semi-definite. Okay. And we also say that H and G are alpha spectral equivalent if basically the two graphs are close to each other in this sense. That is, there exists some scaling C. Maybe you can forget C for now. Like think of if S is less than G and G is less than alpha times H. Okay. But I will have like I allow some scaling here. Okay. All right. This is the same thing as when I say like H and G are alpha cut equivalent. We just really just replace it by cut or flow equivalent. This is the same like really equivalent like analogous notion, right? Okay, and I want to first so the point of telling you about this is really to compare this notion between how to compare the graph using cut and flow. Some times ago we have seen that these two things are kind of the same within log n factor. Within log n. But what about this thing? Like compared with in the spectral way. Is it true that they are the same within some factor again? We want to understand this. Okay. And first thing is that if H is less than G in spectral sense, actually H will be less than G in cut sense. So spectral is stronger than that cut. And why is that? Well, this is because when is it the case where when you say that H is less than G, then it's really like it's just the special case of spectral. When you compare this thing, and you only set X to be 0, 1 vector. Why? Because when when x is like 0, 1 vector, like it's like it represents a set S, then just to recall, this is what exactly? This is just the cut size, right? The cut size. So this is like when you put this as a 0, 1 vector, this is just comparing cut size. But when h is less than g in spectral sense, it's every vector. Okay. Now, can we say something about the converse? If h is less than g in cut sense, can we say that within some factor, h is also less than g in spectral sense? So it turns out that this is not true at all, surprisingly. Like, not sure if it is surprising, but it's not like flow where you still like have some equivalent up to log n factor. Here it turns out that there are two graphs, G and G tilde, where these two graphs are basically the same in cut sense, but they are completely different in spectral sense. So like so this G and G tilde are like the same for cut within 1 plus epsilon. But here, G is less than G tilde is less than G. But G is not less than G tilde even if you allow like something like n factor. So, okay. And this is the example. So imagine that you have this kind of graph where it's basically a cycle. You start with a cycle, and you have n nodes in the cycle, n nodes. And now for each of the edge here, you replace it by a bicyclic. Like you replace each node by k node here, and put a bicyclic of size k by k, and do this for every like step here. Okay, so that's how you get this graph. So, but the next step to construct G, I will just add one more edge here, just to connect this. Okay. So this is just a graph like when n is 8 and k is 4, and then G would contain this edge, but G tilde is the same graph without this edge. Okay. So what you should think about is that maybe k is something like 100 over epsilon. Okay. K is not too small; it's kind of quite big. Yeah. And now you can see that just from the picture, actually, that for every cut in G tilde and G, they are the same, of the same size. Just it can be off just by 1 here, but like it will be like within 1 plus epsilon factor, because one cut. If you look at one cut, any cut basically, it will have size at least something like 1 plus epsilon if you count only this thing. But if you have this one, it might have you might have plus 1, but this is like the same within 1 plus epsilon factor as 1 over epsilon. So in cut sense, they are the same, right? But now we're gonna say that they are really different in spectral sense. So first of all, G tilde will be less than G in spectral sense, just like because G tilde is a subgraph of G. So does anyone see this? Like, it's just that because you look at this, this is just a sum over edges, right? With of something non-negative. And if you add one more edge into the sum never decrease. So any subgraph, for like if you add one more edge, like if G is a subgraph, G tilde is a subgraph of GP, then this thing will be less than this. Okay, so at least one direction is clear, but we want to show that G is not even less than n times G tilde. Okay, like in this sense, G is much bigger than G tilde. Okay. So what do we need to show? To show this, what do we need to do? I need to tell you like just that the x is x such that LG is like much more than this. Okay, maybe like within like n factor. Okay. So and the x that I will define will be defined just like this. So note that x is just like assigning value to each node, right? So how do I assign that? I put all the node in here to be 1, everything here to be 2, 3, and so on. And this is like, here is n over 2. And then from here is 2, and so on. So is the assignment clear? Okay. And now let's just compare these two things. The one for G and the one for G tilde. So for what do you get for G? What you get is that for like note that this is just here, right? Summing over all edges, like uv in the edge, xu minus xv square. So what is the contribution of each edge here to the sum? Just 1, right? Each of them here contribute 1 because they like xu and xv differ just by 1. So this is how, like for all of these edge, you get this. You will get the same thing for G tilde. It's just nk square, both of them. But however, how large is the contribution from here? It will be something like n square. So this is like a really big contribution to the sum from this edge. But G tilde doesn't have it. Yeah, so like I really just say that for each node here, let's say this is u. I put xu to be 1, and the same thing for everyone in this part of the cycle. And then here I just keep increasing by 1, like everyone here get 2 and 3, and so on. And the same thing goes here. All right. Okay. So these purple edge, each of these will contribute just 1 into the sum of xlx for both of them. But the orange one will contribute something like n square. So this is something like n over epsilon square. This is n over epsilon square, but this is n square. So you see, like when epsilon is a constant, this part is like n factor bigger than this one. Yeah. Yeah. So that's the example.
How is the C times the graph defined? Like it's the same way, like multiply all the weights by C.
Yeah. Right. See, you're talking about this definition.
Yes.
Yeah. Just multiply everything by C. Yeah.
No, I can't we include the C in the algebra itself.
Why can't? Sorry. Say it again.
I mean, I don't understand why the definition needs that H prime equals CH.
This is just to make it a bit more flexible. That is, you for the purpose of this lecture, you can ignore C for now. Say that C is 1. But here, I still say that, let's say that I have two graphs, G and 100G. They are just the same graph within by just some scaling. With this definition, I would say that they are the same. Because you can make it equal by scaling. Make them equal by scaling. Yeah. But here you can see that no matter what scaling you put into G theta, you cannot avoid factor of n actually. Yeah. So the point here is just to say that spectral equivalence between graph is strictly stronger than cut equivalence. Can be much stronger sometimes. Yeah. It's not like flow and cut, which are kind of the same. All right. There are some like digression I want to make actually. So by the way, that's the point of this part. Spectral equivalent is strictly stronger than cut. All right. Now that some digression. So if you are given two graphs H and G, can you check if H is less than G? Well, that can be done. Why? Because you just need to check if this is PSD, and that can be done in polynomial time. However, is there any fast algorithm for that? That's I don't know. Or like checking if H and G are are equivalent up to some factor approximately. That's not known too. Something is even crazier for cut actually. So if you are
like near linear time.
Yeah. Or like sub-quadratic time. Yeah. And this is even crazier for cut. If you are given H and G, and if you want to check if H is less than G in the cut sense, well, I don't even know polynomial time algorithm for this. So that's a bit crazy. So how about flow? Flow, this is easy actually. Like you can check this in polynomial time. Why is that? Right. Like it's about like checking multi-commodity flow problem, solving multi-commodity flow problem, and you can solve LP. Yeah. And because you can check this, so you can like you know that if you allow like log n relaxation to this problem, you can solve it for cut. But if you want it exactly, it's not clear. Is it NP hard? I don't know too. So, all right. So, okay, spectral is stronger than cut, but can we still say that all of the expanders are in some sense like spectral equivalents, just like we have done for like flow and cut? Like that is, we said that all of the expander with the same degree profile, they are approximately the same for both cut and flow sense. Now I want to say that this although Spectral's notion is stronger than cut, within expander, they are still the same. Although it's harder to make them equivalent, expander are still like equivalent within this spectral sense. Okay, and well, so to show that, we will start with this lemma. Suppose that G is a phi expander, and H is less than G in degree. Like every node have in H half degree, at most the degree in G. Okay. For all node, the degree, the weighted degree. Okay. In G. Then, just by doing this, we want to show that H should be less than G in spectral sense too. For like, not just for all cut now, but for all vector X. You have that like, this is true within this vector. Okay. So how do we show this? Well, we start by like, we can first assume that H and G have the same degree profile. And that's not hard because we can just always add self loop to H. So that like now they are equal. And why is fine to add self loop? Because, you know, like when you add self loop, the Laplacian doesn't change at all. So it's fine. Okay, so now assume that they have the same degree profile. And what we need to show is just that X, this is less than this within some factor, right? For all X. For all X. So let's look at X where like we will have two cases basically. When X is orthogonal to the vector D, and when X is parallel to D. Okay. Now, what happen when X is orthogonal to D? Well, by Schieger, directly by Schieger inequality, we have it. We have that G is actually more than. So okay, there are actually two steps. By Schieger inequality, we have that this term is at least this term, where D is a degree, the diagonal degree matrix, okay? Within like phi square factor here. Why is that the case? Well, I mean, we know this, right? By Schieger that, so phi is at most this thing. So times 2. And so like phi square is less than this. And then this thing is nothing but this term. So now you just plug in this into this inequality, and then you get this inequality. All right. Good. So next thing is that x dx, like times 2, is also more than x LHX. So you have seen this before, actually, because when you just look at this term, well, and you expand things, you get that this is sum over all h, and this is now like plus here. So this is at least 0. So now combining the two, you get that well, G is actually bigger than H within phi square factor, at least for the vector X that is orthogonal to D. So that's the first case. And now for the second case, when X is parallel to D, it actually reduced to the first case. So why is that? Suppose that you have this X parallel to D. Then what you do first, what I can do, I will just translate X by all one vector. Like I have X and I translate it, the whole vector by all one. I translate it until I get some vector Y such that they are orthogonal to D. Okay. And just from the last case, we have that this thing holds for Y, because Y is orthogonal to D, and we have this case. But when you do translation, like it doesn't change when like X LX and Y LY. It's the same thing. They're the same thing, because the one vector is actually in the kernel, so that doesn't change anything. So because, and the same holds for LH. So this means that this thing holds for X that is parallel to D as well. Question?
So if D is O1 vector, then we already have the case where
Yeah, if D is all one vector, then when you, like, it's just, they are both of them are 0. So the inequality holds. Question? More question?
What was sigma?
Oh, sigma is just some scaling,
Okay.
some constant. Yeah, you just like when you start with some vector X, you can always like translate it so that they are like by some scaling fact sigma, and then they will become, and then you just choose the
In the previous note as well. Oh yeah, I remember this. You did something similar in the previous lecture.
And
as
proof
well.
of legal.
yeah, right.
To prove the hard direction.
Yeah.
Easy direction.
I'm not sure which one. Yeah. I mean, what does it mean? Like, just to make sure that you understand, like, well, what does it mean for Y to be orthogonal to D? Well, it's just like this thing is 0, right? But if it is not 0, like if this thing is non-zero, then if you just choose sigma to be this thing, then when you set Y to be X minus sigma 1, then you would have that this is 0. Like you just translate it exactly so that they are orthogonal to D. Okay. So the point is just when you know that G dominate H in degree, then G will dominate H in spectral sense within some factor. Okay. But from here you can already like conclude that, all right, if both of them are expander with the same degree profile, just apply the above lemma, then you have that G is less than G prime, and G prime is less than G. So they are like basically equivalent. Okay. And for every graph H that is like that are the restricted graph, H will be less than G. So basically you have the same kind of what? What?
Sorry, I'm a little confused.
Yeah.
I don't understand why it was like scaling by one vector instead of like d vector. Like I think you get 0. Maybe I'm wrong.
So
Is d a unit vector, first of all?
D is not unit vector. D is just the degree vector.
Yeah, never mind. I'll go with think about it.
Okay. But this case is fine, is it?
Yeah.
Okay. Yeah. So it's just when you have something parallel to D, and you know that, like, when you translate it by all one vector, that this term doesn't change at all, because all one vector are into the kernel. So you just translate it. Like you have something parallel to D, but you can always translate it so that they become orthogonal to D, and you apply the last case. All right, but anyway, for like, remember this picture, right? You have that if you look at all of the D restricted graph, basically the expander like forms some equivalent class, which and they are like they are bigger than everyone else. And we conclude this for cut and flow, and now they are the same also for Spectral. Yeah. Okay, so that's the picture that I think is good to have in mind. Now, new topic, expander mixing lemma. So let me tell you about some motivation why we talk about this. So let's just look at some graph G with degree profile D. Okay. When you have that, suppose that G has high conductance. We have that for every cut, the edges crossing the cut is close to its volume. That's the definition. So this is about the guarantee about edges crossing one set S. It's between one set, like S and its complement. Okay. And basically this is like, we like this because it's a kind of the same behavior as the product graph, or in some sense, complete graph. It mimics the very well connected graph. They have the same behavior. Yeah. So can we say something about something stronger? That is, what if we say that we look at two sets S and T instead? In the product graph, what would you have? Like the number of edges between S and T would be something like this number, right? Like each of the edge. You remember the definition of the product graph, right? Each edge UV has this weight U over this. But when you sum all pair, you will get this. Yeah. So is it the case that expander would have the same behavior, just like that hold for the product graph in this way too? That's the question. And note that this property is stronger than the one about cut here, because the one about cut is just when you set t to be the complement of s, basically. So this term, when you set t to be complement of s, this term is just like this thing become this equal this. So yeah, basically I want to ask now, like, do expander satisfy this stronger property? And you see that if it does, then it has some application in the next lecture, like for fast algorithm. So so what do you think is the answer? Yeah, so it turns out that if it is if the graph is a expander because of eigenvalue, then the answer is yes. But if you just guarantee conductance, then maybe no. So that's the thing that I want to tell you. So to talk about that, to prove this, we need to talk about some notation. So recall that the normalized Laplacian is just defined to be this way, right? It is just okay, and we have seen that the eigenvalue of normalized Laplacian is between 0 and 2. Now, I want to look at this term basically and call this thing normalized Laplacian normalized adjacency matrix. Okay. So this is nothing but like A prime G is just I minus NG. And because of that, you can infer that like what about the eigenvalue of G, A prime. Like for it, because now you have that this is just 1 minus for every I. This is 1 minus this, right? So now you have that the eigenvalue of A prime is between 1 and minus 1. Okay. Just to repeat things in term of A prime, like we would have that A prime, the second eigenvalue of A prime is 1 if and only if G is not connected. I just rephrase what we have talked about for normalized Laplacian in terms of normalized adjacency matrix, right? So if this one, like second eigenvalue is 1, then G is not connected, if and only if. If this thing is strictly less than 1, then G is a expander. This is Cheeger inequality. And if lambda n of A prime is minus 1, then G is bipartite. So now we want to define this thing, sigma 2. This is just the maximum, the second largest eigenvalue in absolute value of A prime. So you know that the first one is always 1, but you take the maximum guy in absolute value here. That is sigma 2, right? So you take the maximum over all this, but actually you just need to look at the second eigenvalue and the last one actually. Take maximum absolute value of these two. Okay, so that's sigma 2. Okay. Now, what does it mean when sigma 2 is small? Like, so now, so you see like this lambda n can be -1. This one can be 1. But if sigma 2 is less, like strictly less than 1, then it means like G is like kind of far from being disconnect, is being expander, and also far from being bipartite. But what does it really mean actually? So now that's what it really means is that before I go to the statement, it means that when sigma 2 is small, you have this strong property for every 2 set. Now it's about 2 set, not just 1 set. Okay. So the lemma says that for every S and T, a set of node, the number of edges between the 2 set is basically close to this thing, the thing that you expect, but within this term. So if you think of sigma 2 as something small, and it can be as small as, you will see later that it can be as small as, much smaller than constant. It can be as small as like d, 1/√d, when d is the degree like, of the graph. Like, think of it as something can be much smaller than a constant, all right? If that is the case, then you have that for every 2 set, the number of edges here is kind of have the total weight close to the one that it would be for D product graph. Is the statement clear? Okay. So now let's prove it. So what we will prove is to show something which is just to show that sigma 2 can be written in this way. Let's look at it. So it's the maximum over all vector x and y, such that you put x times the adjacency matrix minus the this is just adjacency matrix of the D product graph. R is the adjacency matrix of D product graph. So that is the entry of NTUV of R is this thing. Like in another way to look at this is that R is exactly this matrix. Okay. So that's R, and multiply it by Y. And this is basically something like norm of X, but you something similar to norm of X, but you have this scale by D. The same thing here for Y. All right, so that is just a bit, quite a lot. But let's say that suppose that we have this, then we are done. Why is that? This is because if you look at this expression and you just take x to be a vector for a set S and y to be a vector for a set T, then this now is exactly the number, like you just try to plug it in, right? This is just the number of edges between S and T. This is the total weight of edges between S and T in the D product graph. This is okay. And for the thing below, you have this thing. Oh, maybe it should be this. Oh, but it should be. Right, thanks. Good, thanks, yeah. Yeah, and that would give the lemma. Okay, that would give this lemma. Okay, so now how do we prove this? Well, we can just try to do some math. Yeah, this is the part of the course that there are quite a lot of algebra, but after next week, it will be more and more algebraic. But oh no! Sorry. After this week, it will be more algorithmic. Sorry. Yeah.
All start with A and C.
Both of the terms come from the same person, right? So, what's the name of the guy? Algorithmic. Yeah. But, okay, that's the. Anyway. Yeah, it will be more algorithmic after this, but okay, so let's prove it. Well, I can just take this normalized adjacency matrix. You write the eigenvalue decomposition of it. Okay, and note that the first thing here is 1 because the first eigenvalue is 1. And what actually is the first eigenvector? Well, it's going to be this thing. And why is that? So, because you have seen actually, at least if you remember, that the first eigenvector of the normalized Laplacian is this. But because you can actually verify that this thing times this is 0. And you normalize it so that they are unit vector. It is unit vector. But A prime and N would have the same eigenvector because it's just about like A prime is just I minus this. So they have the same eigenvector. Okay. So we know what is the first eigenvector. So what is sigma 2 then? Well, I just take A prime, and I just remove the first eigenvector from it, like remove it. And now I maximize over the rest of the space. Like maximize V. Okay, this is just the variation, the characterization of the eigenvalue. And it doesn't matter actually that like even if instead of maximizing over V for both sides, I can replace it by Z here and W here. I replace it by norm of C and W. So at least this direction should be clear. Yeah. And we need only this direction actually. Oh no. We need this direction, sorry. So this direction is true too, because the one that maximizes it will be like just the same vector. So, but okay. But I will just we now maximize over both Z and W. And now we change, like just map things so that it becomes something what we want. Like just map Z to be D to the 1/2 times X, and W to be D to the 1/2 times Y. And that's what you get. This thing become this thing. This thing become this. And now, well, you do like you just simplify things. A prime is just this term. So well, this thing times this thing become just A here. And this part, it will become R. And this is just by doing math, but yeah.
Why can the max over Z and W be higher?
Why can this be higher than why is this true? You ask. Well, this needs a proof, but it will be the case that you will maximize this using just one vector. The X is a maximizer where they are the same vector.
We haven't proved that.
We haven't proved it, yeah. But if you think of like ellipsoid, that is just like intuition. It's not a proof, but yeah, I will just claim this without proof. Yeah.
How many consider first equality for sigma 2?
Why this is true? You ask.
And since that's kind of close to the definition of lambda 2 itself, sigma 2.
Oh, thanks. I should put
Maybe plus minus.
maybe I should put this thing. Yeah. Yeah. So this is why I put this thing here. Yeah. Thanks a lot. Yeah. Yeah. So that is just some math, but the point is these two terms are close to each other within this factor, and this factor will be like negligible if sigma 2 is very small. Okay. So if G is like D regular, every node have the same degree D, then you can simplify it to this. Most of the lecture node is presented in this way, like just stated for this, but we show the proof for general graph. And it turns out that it holds, like the converse also holds. So if it is a case that for every set, like if for any regular graph G, if these two things are close to each other within this factor times theta, then sigma 2 will be basically theta 2. So sigma 2 really kind of measure how close, really measure how close it is when you look at the two sets and how the weight of like the edges between these two sets is behave like D product graph. That's what is sigma 2 is about. Yeah. So yeah, I was saying that, okay, when sigma 2 is small, it's kind of far from being disconnect and far from bipartite, but that's too vague. What it means is this thing. That's the meaning of sigma 2. Okay. So now for this part, section 4 here, let me simplify the discussion a bit, and let's say that graph is D regular. Okay. So we were saying that like I wanted to ask you like how small sigma 2 can be. So if sigma 2 is 0, then like it's like this thing holds, right? It's a product graph, but actually it turns out that sigma 2, well, when your degree is not like, if degree is not d, is not n, all right? If the degree is d, then sigma 2 can be as small as this thing. And also there is like this is tight in some sense. So that's what we want to talk about. So basically, if you take like, there is a proof which says that if you have given any n0 and d0, then you can find like n and d within this, which is kind of the same as n0 and d0 within some constant factor. So there is n and d such that they exist the d regular graph with n node. And sigma 2 is as small as this thing, 1 over root d. Okay. So it was actually like, it means that like people know how to construct the graph that such that sigma 2 is so small. Like the graph is so well connected for every d, basically. For every degree d, you can find this very strong expander in eigenvalue sense when d is as small as this. When sigma 2 is as small as this thing. So this is known for like, but
Can we also construct it like faster?
yeah, like the construction is usually like algebraic, but so there is like some formula for it. Yeah. I'm not sure about like how explicit it is. That is, if I say that I want n to be like of exponential size, and I just say that I query 2 nodes, isn't an edge between this node? Can I answer it in time which is like polylog time, polylog in the size of the graph? Can we do that? That's I'm not sure. But basically, we can, like, people ask actually if you can remove this thing. So can it be true for every integer n and d? Not just like choose n0 and d0 and find something close to n0 and d0. People don't know that. But this is like some deep question, like some progress on this. Okay, I mean, these people basically prove they can remove this thing, but they prove something which is like bipartite version of this this theorem after removing this thing. But what I mean is that they will have that the lambda n is still like -1, but everything else except the first lambda and the last lambda, these are now small. Yeah.
So if sigma 2 is small, does it mean that the graph has constant conductance as well?
Say it again. If
sigma 2 is small, does it mean the graph is a good expander as well?
Yeah. So if sigma, actually if sigma 2 is just like less than, strictly less than 1, then phi is constant. But here it said that it's not just strictly less than 1. It's like way more than 1. Yeah. Note that sigma 2 less than 1 implies that, actually, it just implies that lambda 2 is, it's not if and only if. It just implies that lambda 2 is more than some constant. And this is now if and only if. Because sigma 2 is about lambda n as well.
Lambda, here you're talking about the normalized adjacency.
Right. Thanks. Yeah. Okay.
The normalized Laplacian.
Yeah, normal Laplacian. Yeah. All right. So this is already strong. Like, this already means that the graph is an expander. People can do it such that it's so expanding. Yeah, like much smaller than 1. I mentioned this, that like people can even, like they prove a partial result for this question for bipartite case, but even that like lead to something very cool which I don't understand. Something called Cartesian-Singer problem. Some deep math question, but it's not a big deal, which I don't know why. But yeah. Anyway, so can this be smaller for every d? Like can there exist a theorem which says that this is actually something like this? Now it turns out that it is impossible to prove something like that because of this theorem. Actually, for any d regular graph where d is not too big, it's not like n, it's not like complete graph. Okay. When d is like not too big, then you actually need to have that sigma 2 at least need to be at least 1 over root d. And the proof actually is quite simple. So let's just look at the proof. Let's look at trace of, if I take the trace of a prime square, this is the same thing, like the trace is the same thing as a sum of eigenvalue. So the trace of the matrix square is just sum of the eigenvalue square. Okay. And now let's expand this term. The first one is 1. And everything else in this term is less than sigma 2. But it is squared, so you have sigma 2 square. And there are n minus 1 here. But, okay, so we just rewrite things, and we get some low bound of sigma 2 in terms of this trace. So let's interpret what is this trace. So, first of all, instead of looking at a prime, let's look at a square. So the entry uv of a square is really just a number of two-step walk from u to v. Right? So, well, I will just take this exercise. Like every two-step walk, when you multiply a and a, and you look at the result at u. Yeah, think about this. Yeah, this is just the number of two-step walk from u to v. But if you sum up the trace, like if you look at the trace of this, what is this? Well, it's just a two-step walk for you from u to u. which is what? It's just you have a graph here, you have U. How to like go from U to U in 2 steps? You can only go to U neighbor and back. And so there are like many way to do it. So D for each node. So that is N times D. When G is D regular, like the normalized adjacency is just A over D. So the trace here is just this thing over D square, which is N over D. Now you plug this thing into the formula, then you get that, you get this thing. So when D is not too big, if D is N like a clique, then this doesn't tell you anything. But when D is less than N, then this term is at least 1 over root D. Yeah. So you have that when D is not too big, you indeed have some lower bound on how small sigma 2 can be. When it is a clique, sigma 2 can be 0, right? Because like for D product graph, you have seen before that for D product graph or a clique, this is, you have that this exactly is the case, like it holds exactly. So, okay. All right, so that is Ramanujan graph, and you know that is tight. But let's look at some property of it to get some intuition, and we will use this property next time too. So it's just an easy application of expander mixing lemma. So if I take, let's say G is a D regular graph, and let's say we take any 2 set, and the 2 set are like big enough. Like this thing, the size of S times size of T times D is bigger than N squared. Then I claim that there must now exist some H at least. Before going to the proof, let's look at some example. If you have graph G and degree is root N, take any set which is not too small. Both of them have size like n to the 3/4. From here, you would have that there must exist some H between S and T from this. Okay. And actually, if S and T are like just a bit bigger than what you need to conclude that the number of edges between them is non-empty, you actually would have that the number of edges between them would be this term, which is, it will be this term, which is like O of n. This is just some example, like that is all the, like for a clique, if you take any 2 set, always there is an H between them. But here you don't quite have that, but at least you have that. If you take 2 set, which is big enough, still quite small, but big enough, then you will have an H too. You can conclude that. If the graph is like Ramanujan or have very small sigma 2. So let's just prove this. I want to prove that if S and T are big enough, then there must exist an H. So let's prove contrapositive. That is, suppose that there is no H between S and T. So expanded mixing lemma for the regular graph says just say this thing exactly with node. and you just plug this to be 0, then you have this thing, and then it just rearrange, you get this. Right. So yeah, any two set which is big, you have an edge. You also have that if the graph is Ramanujan, then the independent set cannot be large. So in a clique, independent set can be at most 1. But in Ramanujan graph, you have something which is non-trivial. You have that can be at most n over root d. And why is that? It's just because if you just apply this corollary when S and T are the same set, then you need that in any independent set, then there is no edge inside it. So the size of S need to be at most this by this lemma. Yeah. So S can be at most n over root d. There is some exercise that I will talk about later on Friday. And before we finish today, now let me conclude something. Now this is where we really see, okay, Shiger says that conductance is big if only if lambda 2 of normalized Laplacian is big. So that's a rough message. We have that. But in the regime when the graph is very well connected, the two things are actually incomparable. So we just have seen when eigenvalue can be stronger than the eigenvalue can be stronger than conductance in this way. So let's say that conductance is so let's say that you even have very strong conductance. It's almost 1, almost maximum. I want to say that even this, you wouldn't have something that is guaranteed by small sigma 2. You wouldn't have what you have from expanded mixing lemma. Okay. So yeah, even you have that conductance is very strong, we cannot conclude that this is the same. This approximately holds. And the example is you just take a star, conductance is 1, but yeah, you can just look at these two sets. There is no edge between them at all, even if the two sets are as big as n over 2. And if you look at in general graph, if you take Shiger inequality, even when conductance is 1, Shiger inequality would tell you that lambda 2 is at least half, which means that sigma 2 is guaranteed to be only smaller than 1/2. It's not 1 over root d, just 1/2. And when you only have this guarantee that sigma 2 is less than 1/2, you can check actually that when you try to apply expanded mixing lemma, it doesn't really tell you anything strong. Yeah. So that's the case when you have really strong conductance, you don't have what is guaranteed when sigma 2 is small. Okay. So eigenvalue can be stronger than conductance. Let's look at another way around. Suppose that the graph is deregular and sigma 2 is as small as possible already. So you would have that lambda 2 is this much. is larger than 1 minus this. But again, by Shiga inequality, you can only conclude that conductance is more than half. It's not like close to 1. So what you can get from Shiga is not as strong as you want. You don't get this. By the way, why do we care about this? So when the graph is irregular and the conductance is actually close to 1, there is a name for it actually. That is, they call it lossless expander. And you should think of D as something small, and G should be regular too. Otherwise, it's going to be easy to get a large conductance. Why? Because if you allow D to be big, then a clique would do it. And if you allow G to be not regular, a star would do it. So it's easy to get that. But if you have both of them here, D is small and G is regular, then it's not clear actually what graph give you, can you construct lossless expander? It's not clear. Even bipartite version of this is important, but I will not define it. Very important in complexity theory. So there really are a lot of application of lossless expander. In complexity theory, in streaming algorithm, even in dynamic algorithms, we just recently found some application. So one of the possible projects is actually to just write, do some survey about the state of the art of lossless expander and the application. I think that would be quite interesting. It's a very strong object, and even how to construct it is very interesting. There's some paper about it. Yeah. By the way, if you know about streaming algorithm, usually, if you have heard of it, I will just be brief about this. But most of the streaming algorithm is randomized. Otherwise, you cannot get anything done meaningfully. And moreover, it's not just randomized. It works only against something called oblivious adversary. That is, you can assume that the adversary doesn't see what is going on at all. It's just give you some sequence of update, and it just cannot generate update adaptively to your answer. So it turns out that using lossless expander is a way to make some of streaming algorithm deterministic. There is some very non-trivial streaming algorithm that can be made deterministic, and that use lossless expander. Okay. Next time we will see how to use Ramanujan graph to compute vertex connectivity of a graph faster than a trivial way. So just on Thursday. Thanks.
There are a lot of variants of definition of expanders, right?
Yeah.
So is that possible? We would define a expander and make it as strong as the levels and expanding.